Right, ladies and gentlemen, good afternoon and welcome to this track on hearing and health here at the High Tech Summit at DTU. My name is Anders Høgh Nissen, and it is my honor and my pleasure to be the moderator of this event today. But much more importantly, the track is hosted by the Danish Sound Innovation Network, a hub for research environments, businesses, public organizations, policymakers, and professional users alike. The network has a few focus areas, and one is sound and healthcare, which is, of course, why we are here today. So thanks to the Innovation Network, Danish Sound, for putting together an impressive lineup of both scientists and business people. And I think we're well prepared for some great stuff from the intersection of health and hearing research and markets here today. So as you've probably seen, first we'll have three presenters, and then at 3:25 p.m. We're having a fireside chat without a fire, apparently. And that will be with representatives from the industry, and I'm really looking forward to that as well, as we're going to be talking at the fireside chat about the current state of the technology and the future trends, and as well as the opportunities and challenges for the established players and the newcomers and startups in the sound area as well. I should say that after the event, there's a reception. You're very welcome to join us for a drink. It's sponsored, or at least hosted, by Widex and Oticon, and it's after the track at 4 p.m. So, first off, we have 3 talks on sound processing, on hearing and health research, and on the use of machine learning and data crunching in the area of hearing and health. So, without further ado, please welcome Professor Torsten Dau from DTU Electro, who will be talking about bridging the gap from sound processors to brain processors. And please give Torsten a warm welcome.
Thank you, Anders. So, good afternoon, and thanks for coming. Nice to see all of you here. I have 20 minutes to entertain you a little bit about this topic, bridging the gap from sound processors to brain processors. And I'm here at DTU. I'm head of the hearing systems group at DTU Electro. And we are about 45 people there, including 20 PhD students. There's quite some focus on research and education in our group. And we deal a lot with such conditions here, with communication in noisy conditions, or noisy environments, for several reasons. And this is, for example, a sketch of a cocktail party-like scenario at DTU. One of the challenging questions is what makes the intact, so the healthy auditory system so robust in such situations, or in a restaurant where we almost effortlessly can follow a talker or can segregate between different speakers. While in contrast, hearing-impaired people are often challenged in such situations, and this is another challenge to understand. So what makes the intact auditory system so robust? And this shows here an example of that's a representation of a speech signal, a spectral-temporal representation of speech signal. That's the frequency axis, time axis of the original sound. You see formants, and the red structure shows the energy of the speech signal across time and frequency. And this is on the right here, a brain response, so to speak, the information of the signal represented in the brain, also in terms of spectral and temporal representation. And that looks pretty similar here. So what is interesting now, if we put the signal, the speech signal, in noise, and then you look at the spectral temporal representation of that mixture, then you see still the speech signal, and you see the noise floor here. And that's, so to speak, also what enters the ear, this noisy representation. What you show here in healthy people, or in the healthy auditory system, that's the representation in the brain of this noisy mixture. But it looks pretty clean here, almost like this one, without any noise in the input. So what happens here is, in the healthy auditory system, there's some kind of noise suppression algorithm, or noise suppression going on from the ear to the brain in the healthy system, which is astonishing. And the details of that are not understood. In contrast, hearing impaired people apparently do not have such a clean representation. Their brain, there's a lot going on, and it's difficult to fix, so to speak. That's the challenge. So the challenge is how we can create such a robustness with aided hearing. So via hearing instruments like hearing aids or cochlear implants or other aids. And why is the normal hearing system or normal hearing people, why are they so robust in noisy situations? So we have these sources here, and what we enter here, what we have in the ear canal is the mixture of these different sources in one-dimensional sound pressure variation as a waveform. And so one reason for that robustness might be that normal hearing listeners can selectively attend the sound to the sound of their interest while suppressing irrelevant information. In contrast, hearing impaired people are typically challenged in these situations despite hearing instruments. Despite amplification, they often have these challenges. And so why do hearing instruments are modern, are powerful, can a lot, but they also have challenges in certain situations like these. And so why do hearing instruments have challenges? Well, first of all, they're still hearing devices. They are sound processors, not brain processors. And whereas normal hearing people or the normal hearing system involves an active cortical process or mechanism that focuses on behavioral relevant sound sources. And this is what the instrument typically cannot do yet. And so, as I said, we have several sources here. They add up, enter the ear canal. And what can we do in order to separate or segregate between these sources to be such that it becomes easier to differentiate between them? So for example, so we have these sources. They generate some neural representations of the brain, all of these different, let's say 3 sources or speech sources, and then create some neural internal representation. And the question is, can we, via attention to one of these speakers, so to speak, suppress or enhance this one or suppress the other activity such that we can, through also hearing instrument, via feedback, closed loop structure, amplify the attended speech source. And that's the idea of a relatively new European project, research project, which is called COCOHA, which stands for Cognitive Control of a Hearing Aid. And this is a collaboration of several partners, which focus both on acoustic scenes, relevant acoustic scenes, which I will get back to in a minute, where we test these things. Then also acoustic pre-processing for sound separation via microphone arrays, for example. Then there's quite some focus on EEG measurements in hearing impaired people and normal hearing people. And in particular, there's also focus on what we call EEG decoding algorithms. So what is the link between the EEG, the neural patterns on one hand, and the acoustic features or auditory features on the other hand? And then there's also an important part, even if we can do that, how can we, so to speak, do it in a modern hearing instrument such that we avoid these plenty of electrodes on the scalp, but potentially do it with electrodes in the hearing instrument? So the approach is, it's about decoding selective attention with so-called single trial EEG, which means single trial means it's not an averaged activity, averaged many times. It's a single trial. It's just the single representation of the EEG from which we try to extract the relevant information. So from which talker we are attending to. So the approach is to find a robust mapping, so a relation between auditory features or acoustic and auditory features on one hand, and the human EEG on the other hand, so the EEG data on the scalp. And so in the training phase, typically the task of the listeners is to focus, let's say in a scenario with 2 ongoing speakers, to focus on one or the other at a time, and then switch if you want, and then to find filters, which is the relation between the EEG activity and the acoustic representation or the auditory representation. Yeah? And so we have an unattended and an attended speaker, and then there is some, what we call here, auditory representation of speech. So this is the representation of the acoustic signal in the auditory system. And then we would like to link this to the measured EEG response. And then there's this decoding process from here to there. That's decoding. From here from left to right would be encoding. So here there are this decoder, which it tells us if we are now focusing on the attended one or not. And then in the test phase, so this is then to record more data in a number of listening scenarios, where then the task is to reconstruct the attended speech, either 1 or 2, and based on the neural data we record here. And then to detect which stream is attended by comparing the neural reconstructions with features of each stream. So the idea is to really reconstruct the speaker based on the neural representation we measure in these on these electrodes. And one challenging question, of course, many people are skeptical with this. It works surprisingly well. And one challenging question is, of course, does it work in hearing-impaired people? Does it work in noisy environments, really, if you do not have just two clean speakers, but noise conditions, reverberation, and other aspects? So we test this currently, and that's quite some focus on real-time scenarios, where often we know that normal hearing listeners are quite robust. They are good at that, despite stimulus degradations, like reverberation. And the question is, how can we track the attendant real-life scenario, or scenarios, with these neural correlates? How robust is this really in realistic situations? And rather than recording EEG in the outside world and so forth, we bring the real world to the lab and reconstruct multi-talker scenarios in the lab. That's a nice tool we have, and simulate any virtual audio environment with varying amounts of reverberation, for example. It could be a church, could be a classroom, could be whatever we want and find relevant. We can, so to speak, build. And this is done, and will be done also in the next future, in order to capture and reproduce realistic scenes, so to speak, to take the auditory and visual reality into the lab. For example, this is a railway station situation. We try to reproduce this in the lab in order to study such a condition or many others. In order to study perception in complex environments, but also to develop and evaluate new hearing instrument algorithms, because this is what we want to test in such relevant situations. So this is done, for example, either via simulation software, so we can simulate any scene or room, like this one here as well. Or it could be, if it's more complex and a dynamic scenario with various sources varying in time and space, then we can use realistic recordings, and then can use ambisonics technology to reproduce the sound field in a given sweet spot in the lab, and to have exactly the same acoustics as we have at the railway station or where we want to be. So we can construct restaurant situations or cocktail parties, and then can study performance measures like speech intelligibility, scene awareness, localization, or whatever it is, speech identification. Looks like this, which we have over there. And so I talked about decoding, so how to read out, and this works actually surprisingly well. It's fantastic to see from a fundamental point of view as well, and also from the potential of applications. There's another aspect. We are not only interested in decoding, so reading the brain and learning from that what about the sound, but also how is the other direction, encoding, how is the acoustical signal represented in the brain, and how are consequences of hearing impairment represented in the auditory system and in the brain. That's important to know and to understand in order to optimize solutions for the individual listener. I get back to that. So we do listening experiments to learn about the individual listener's performance in a given task, and we have physiological knowledge. And what we do, and this is just one example of a computational model. So most of us are engineers or physicists. We try to mimic the signal processing in the ear and in the auditory brain, so the transformation from the acoustical waveform to some percept, and go through, that's the input here, the acoustic input, and then there is some processing through filters, bandpass filters and other aspects in the outer ear, middle ear, the inner ear, so in the ear and also beyond in the auditory brain, represented by certain filter stages here as one example. So we have these two aspects, and one focus at the moment is to try to mimic also individual hearing loss and also consequences of individual hearing loss for perception, like speech identification. So So, and then we need to make assumptions about what's going on, or where the deficits are in the individual listener. Typically are sitting in the inner ear here, and I do not go into details here, but they can also be located higher up in the system. There could be cognitive processing deficits and other aspects. And this is important to try to mimic, because we, as an engineer or physicist, we would like to describe nature and would like to predict behavior. And the more we understand, the better we can apply such knowledge. And also, one of the major aspects of modeling is often we would like to predict speech intelligibility performance in a noisy restaurant or in whatever condition we think is relevant. And then we need a transformation between the acoustic input, again, the speech signals, the background noise and so forth, transform that through some processes we assume happen in the ear and in the brain. And then we transform that to percent correct, for example, so and so many percent understood words in a sentence, right? And the better we are, the more we can use it for evaluation of hearing instrument solutions, for example. So we need, and we are working on it, and many do, try to link the acoustics to the perceived output of the, for example, intelligibility. And that's the basis for, also evaluating effects of hearing aid signal processing, like amplification, like compression, like beamforming, other aspects. What is the effect? Can we predict it? And if so, then we have understood quite a bit, and then we can optimize that. So in the last part of the talk, I will talk about how can we so compensate for potential difficulties in the individual listener. So this is an example. It's a teaser, so to speak. We have here what is called audiograms. So this shows us the sensitivity to pure tones as a function of frequency. And these are 7 listeners only in this particular study, 7 hearing impaired people who have good hearing at low frequencies up to 1 kilohertz and bad hearing at high frequencies above 1 kilohertz. But they all have the same audiogram, more or less. So what we see on the right is 2 additional measures. So this shows here a measure how good people are at discriminating different frequencies of tones, simple tasks. So discriminate 200 hertz tone from 200 plus X hertz. And this is bad, and this is good. This is normal hearing performance, and these are the 7 different hearing impaired people. And you can see here they are largely different. So some people have no way, they cannot discriminate 200 hertz from 250, and others are like normal hearing listeners. And this is here speech intelligibility prediction and noise. And again, so this is poor, this is bad, and this is very good. So some are close to normal hearing, and some are very poor. So this is a fact, despite the fact that all of them have the same audibility to sensitivity to tones, which you measure in the clinic, and on which basis you get a hearing instrument fitted. So despite similar sensitivity to tones, the other hearing abilities can vary greatly across people. That's a challenge. That makes it also interesting, right? I mean, it's not so homogeneous, simply. So this means, of course, the logic is that amplification alone is impossible to solve these people's challenges. Because if we do the same amplification, which we should based on the audiogram, then they should all get the same hearing instrument in principle, but it doesn't work. Some people are happy, others not, based on other abilities. So, and this is, so to speak, nowadays is current clinical practice to base the so-called auditory profile only on the audiogram, this pure tone sensitivity, and then the hearing aid process is done via a more or less trial and error process in order to optimize the aided performance based on this amplification only using the audiogram. Right? Despite the fact that we have fantastic hearing aid technology, and we have quite some knowledge about the hearing process itself. So there's this project BEAR, which is supported by the Innovation Foundation, which is in collaboration with Danish 3 hearing aid companies, plus Danish universities, plus the clinics, where the attempt is to provide a true auditory profile, which is characterized not only but also whatever this is, and then we collect a number of data which allows one to classify among people, and this leads then to a hearing proposed to be leading to a hearing aid fitting process, which is more advanced because it's based on individually data guided process, which then also based on another test for evaluation, which characterizes not only the audibility loss as given by the audiogram, but also reflects what is called distortion loss. So imagine also in the visual domain, you could say if you have a milk glass and you amplify the intensity of the light, then it makes it lighter and you can then see it, but it doesn't become clearer. So we need to do something which makes the sound clearer and perceivable. Otherwise, people can hear sound but not understand speech, right? So this is one of the aspects. So this distortion loss must be characterized. And the idea is, the hypothesis behind this project is, or one of the hypotheses, is that we have more dimensions to characterize, and that's really crucial, at least these two. So let's say there are two dimensions of distortion type, 1 and 2. One is probably related to audibility as well, and the one is not related to audibility per se. And so the idea is that there are 4 profiles along these dimensions, such that we have, let's say, profile A, B, C, and D. This one is the best because the normal hearing people sit here. They have no distortion in either domain. The worst situation is here where you have distortions in both domains. And the hypothesis is that probably this domain here, the distortion type 2, is related to temporal resolution, so the ability or disability to process timing, while this dimension here is related to the ability or disability to process spectral resolution or process spectral information in the sound. And so this would be, as I said, normal, corresponding to normal hearing. There's no one. They have no deficits. And on the right here, we have, let's say, or what is called hidden hearing loss. Hidden because you cannot see it in the audiogram. You have normal thresholds, but you have a large aspect of distortion type 2. They still have problems with speech and noise in a restaurant situation, typically. And it's hidden because it's not seen in this audiogram you measure. But we need to figure out what it is in order to help them. So the big idea here, our hypothesis is in that project to come up with the right strategies. Let's say, assuming there are these 4 profiles which characterize an individual listener, and this means each individual listener, each of you, should be represented by 1 point in this plane. And then the idea is to come up with a scenario with a hearing aid instrument strategy which fits or provides the best solution for that particular person in that particular corner or where he or she is. This could be, for example, frequency selective amplification. This could be spectral contrast, whatever this is in the details, which is what we try to figure out together. This could be signal-to-noise ratio improvements we need to provide, otherwise we fail. Or it could be a combination of things. And so the hypothesis is that optimized hearing aid processing can be achieved for each individual profile. That's what we have to test on a large scale basis. And then we can evaluate also these aided strategies in relevant, realistic listening situations. That's also what we will do. So, our last slide. So this means, but still there's a lot of controversy about the best approach. This is a challenge. We have, first of all, the challenge of the cocktail party problem. We don't know what's really underlying it. Both in the normal hearing system, we have an idea, but it's still challenging to really understand what's going on, what creates this robustness. And we have the challenge of what is it what makes the people hearing impaired beyond just sensitivity loss? Yeah, what do we need to do in order to repair that, or to do what we can do with hearing instruments? So we need to know that. But the question is, should we focus on compensating for hearing impairment in the ear, because most people have the problem in the inner ear? So should we focus on understanding that source of the problem, or should we, as I mentioned in the first part of the talk, should we better focus on central aspects like cognitive functions, memory, effect of auditory training, effect of aging, which could help, right, without understanding the details of the cochlear hearing loss? Or should we better consider black box statistical machine learning approaches to optimize our hearing instrument design? We will hear more about this later on, so that we collect input or knowledge via large data, which helps us to learn what is essential. So these are different approaches. And it's probably a combination of different strategies which contribute to finding the best solution for the individual listener. And that's what we really have to do in the future. It's still a challenge, of course, to solve what we call the cocktail party or restaurant problem. So that's what I wanted to talk about. So thanks for your time and attention. And hopefully you find this a little bit inspiring.
Thank you very much, Torsten.
Questions now or later?
I think questions later if we have time.
Sure.
So I'll leave it up to you to get the headset moved around. We'll hear everything that's going on right now, which is great. I'll try to distract you from what's going on over here by walking over here and letting you know that what I took away from the talk, apart from all the interesting sciencey stuff, was that you're apparently, as humans, very well adapted to suppress what you find irrelevant, which I guess means that none of you will remember anything I've said today, which is fine by me. I'm just letting you know that it's okay by me. And yeah, so I hopefully managed to distract you, and we have the next presenter ready.